In the autumn of 1882, the city of Worcester, Massachusetts wore its season like a quiet garment. Maple trees lined the streets, their leaves shifting from deep green to amber and crimson as October settled over the hills. The air carried the cool scent of wood smoke from kitchen fires and the faint rustle of horse-drawn carriages moving along the cobblestone roads. In a modest clapboard house on Maple Street, a boy was born who would one day reach for the stars, though on that October day, no one could have guessed such a destiny. The house stood unassuming among its neighbors, its windows reflecting the pale New England sky, its rooms warm with the simple comforts of a middle-class family at the close of the 19th century. The Goddard household was a place of quiet industry, a father who sold books and kept a small machine shop, a mother who tended the home with gentle devotion, and soon, a child whose frail health would keep him close to the fireside for much of his early years. Robert Hutchings Goddard was not a strong child. From his earliest days, he suffered from colds that lingered, from a chest that seemed always too weak to draw a full breath. While other boys ran through the fields and climbed the tall oaks outside town, Robert remained indoors, propped against pillows by the window, watching the world through glass. His mother, Fanny, brought him warm broth on a tray and placed cool cloths on his forehead when fevers rose. The house grew quiet around his illnesses, as houses do when a child is unwell. Footsteps softened, voices lowered, the clock on the mantel ticking with patient regularity. This quiet world of the sickroom became Robert's first universe, a small cosmos bounded by wallpaper patterns and the view of maple branches swaying against the gray Massachusetts sky. In that stillness, the boy learned to turn inward, to let his imagination travel where his body could not. Books became his windows to wider worlds. His father, Nahum Goddard, brought home volumes from the bookstore, leather-bound editions with gilt lettering on their spines, their pages carrying the scent of ink and paper. Robert devoured them with the hunger of a mind that had nowhere else to roam. He read about electricity and magnetism, about the gaslights flickering in distant cities, about the great locomotives that crossed the American continent trailing plumes of steam. But it was the stories of other worlds that seized his heart most completely. Jules Verne's From the Earth to the Moon entered his hands when he was still very young, and the French author's vision of a projectile hurled from a giant cannon toward the lunar surface ignited something permanent in the boy's imagination. He would read the pages over and over by the dim light of an oil lamp, his small fingers tracing the illustrations, his lips forming the words of spacefarers and astronomers. The house on Maple Street grew darker as evening fell, and Robert would often sit in the parlor with a book open on his lap while the fire crackled in the hearth. Outside, the maple leaves continued their slow descent to the ground, piling in drifts of gold and russet along the fence line. The neighborhood settled into the rhythms of a New England evening, neighbors pulling curtains closed, dogs curling on porches, church bells tolling the hour in the distance. Robert's mother would come to light the lamps, her shadow moving across the walls, and she would pause to look at her son's face, illuminated by firelight, lost in some faraway place. She understood that her boy was different. He spoke little of games or sports. Instead, he asked questions about the stars, about what lay beyond the sky, about whether a man could ever travel to the moon. These were not the questions of an ordinary child, and she answered as best she could, stroking his hair and telling him that God's creation was vast beyond measure. The Goddard family had roots deep in New England soil. Robert's grandfather had been a farmer and a machinist, a man who understood the workings of tools and the patience required to shape metal and wood into something useful. This practical heritage flowed through the household like a quiet stream. In the small workshop behind the house, Nahum Goddard kept lathes and tools, and when Robert was well enough, he would wander out to watch his father work. The smell of machine oil and sawdust filled the cramped space, and the boy learned the names of wrenches and calipers, learned how metal could be turned on a lathe until it gleamed, learned the satisfaction of building something with one's own hands. These lessons settled into Robert's bones, and they would serve him in ways he could not yet fathom. The boy who dreamed of space also learned to shape the materials of Earth. As the years passed, Robert's health remained fragile. He missed long stretches of school, falling behind boys his age who moved through their studies in orderly progression. Yet the solitude that might have stunted another child seemed only to deepen his capacity for wonder. In the long afternoons when he could not rise from his bed, he studied the way sunlight moved across the ceiling, marking the hours with its patient crawl. He listened to the sounds of the house, the creak of floorboards, the distant murmur of his parents' voices, the wind stirring the maple leaves outside his window. These things became the fabric of his inner life, the texture of a childhood defined not by action but by observation. He was learning, though he did not know it yet, the patience that would one day sustain him through decades of painstaking work. On clear nights, when his health permitted, Robert would stand at his bedroom window and look up at the stars. The sky over Worcester was not yet dimmed by the electric lights that would soon transform American cities. The Milky Way stretched across the darkness like a river of diamond dust, and the boy would stare until his neck ached and his eyes grew heavy. He knew the names of the constellations from his reading: Orion the Hunter, the Great Bear, Cassiopeia on her throne, but the names seemed insufficient to contain the mystery. What were those points of light, really? How far away did they lie? And what would it feel like to rise from the earth and travel toward them? These questions followed him into sleep, drifting through his dreams like the smoke from the chimney that rose past his window and dissolved into the infinite night. October the 19th, 1898, dawned over Worcester with the kind of crisp, golden clarity that only a New England autumn can provide. The leaves of the cherry tree in the Goddard backyard had turned a brilliant scarlet, trembling slightly in the morning breeze that carried the scent of dry earth and the distant promise of winter. Robert Goddard was 16 years old that day, still slight of build, still prone to the coughs and fevers that had plagued his childhood, but filled now with the restless energy of adolescence. He had been reading H.G. Wells' The War of the Worlds had recently been serialized, and the British author's vision of Mars and space travel had taken root in Robert's mind like a seed in fertile soil. The book had stirred something that his earlier readings of Jules Verne had only begun to awaken, a conviction that space travel was not merely a fantasy but a problem to be solved. In the backyard of the Goddard home stood an old cherry tree, its branches reaching upward in a tangle of dark bark and bright leaves. Robert had climbed that tree many times as a younger boy, finding in its branches a perch above the ordinary world where his imagination could roam freely. On this particular afternoon, with the low autumn sun casting long shadows across the grass, he climbed again. He settled into the crook of a sturdy branch, his back against the trunk, and looked out over the rooftops of Worcester spreading below him. The town lay quiet in the amber light, church spires rising here and there, columns of smoke ascending from chimneys, the distant glint of sunlight on the waters of Lake Quinsigamond. It was a scene of perfect New England tranquility, the kind of moment that seems suspended in time, and in that moment, something extraordinary happened inside the mind of the 16-year-old boy. He thought about H.G. Wells and the trip to the moon. He thought about what it would take to build a machine that could leave the Earth's atmosphere, that could carry a human being into the void between worlds. And then, suddenly and with a force that would stay with him for the rest of his life, an image blossomed in his mind. He saw a vehicle, not a cannon shell like Jules Verne's projectile, but something slender and purposeful, rising from a field. He saw it accelerating upward, climbing through the clouds, pressing on into the dark beyond the sky. For a brief, crystalline moment, the entire vision presented itself to him complete, a rocket that could navigate the vacuum of space, that could carry instruments or perhaps even people to other worlds. The idea was not a vague daydream, but a technical vision, a problem whose solution he could almost glimpse in its entirety. Robert sat in the cherry tree for a long time after that vision faded, his heart beating fast despite his stillness. He understood, with the strange certainty that sometimes visits the young, that he had been given a purpose. He climbed down from the tree slowly, his feet finding the familiar footholds in the bark, and when his shoes touched the grass, he felt that he had descended into a different world than the one he had left. The backyard looked the same, the fallen leaves scattered across the lawn, the old fence weathered and gray, the family home standing quiet in the afternoon light, but everything seemed charged with new meaning. He went inside and found his diary, and there, in the careful handwriting of a thoughtful teenager, he wrote down the date, October 19th, 1898. He kept that date sacred for the remainder of his life, marking its anniversary year after year as the moment when his true work began. The months that followed the vision in the cherry tree were not easy ones. Robert's health continued to trouble him, and his irregular attendance at school meant that he fell further behind his peers. In 1899, he was diagnosed with tuberculosis, the same wasting disease that had afflicted his mother for years. The diagnosis would have broken the spirit of a less determined young man, but Robert seemed to possess a quiet resilience that illness could not erode. He spent long stretches in bed, staring at the ceiling, but now his mind was occupied with equations and sketches. He filled notebooks with calculations about the forces required to lift a mass against gravity, with rough drawings of rocket nozzles and combustion chambers. The tuberculosis forced him to rest, but rest gave him time to think. His body might be confined to a sick room, but his mind traveled constantly among the stars. In the early years of the new century, Robert's health gradually improved enough for him to attend South High School in Worcester. He was older than his classmates, nearly 20 when he graduated in 1904, but his years of solitary study had given him an unusual depth of knowledge in mathematics and the physical sciences. His teachers recognized a fierce intelligence behind his quiet manner, a capacity for sustained concentration that set him apart. At his graduation ceremony, he delivered a speech titled On Taking Things for Granted, in which he urged his listeners to question the accepted limits of human achievement. The audience applauded politely, unaware that the thin young man at the podium had already dedicated his life to proving that humanity could reach beyond the boundaries of its own world. After the ceremony, Robert walked home through the streets of Worcester as the June twilight gathered around him, the maple trees now fully green, the air warm and soft. That autumn, Robert Goddard entered Worcester Polytechnic Institute, a technical college just a few miles from his childhood home. The campus was a cluster of red brick buildings set among lawns and walkways, and inside its lecture halls and laboratories, Robert found himself among people who shared his passion for understanding the physical world. He studied physics under professors who recognized his unusual gifts, and he spent long hours in the library, working through the mathematics of propulsion and ballistics. In the evenings, he would walk the quiet streets around the campus, his hands in his pockets, his mind turning over problems of thrust and fuel efficiency. The other students saw a reserved young man who kept to himself, but those who looked closer might have noticed the intensity in his eyes, the sense of a purpose that burned quietly but steadily beneath his calm exterior. The vision of the cherry tree never left him. Through the years of study, through the long nights of calculation and the patient accumulation of knowledge, he carried that moment like a private treasure. He told almost no one about it, sensing perhaps that the world was not ready to hear about rockets and space travel from a young man who had yet to prove himself. But in his notebooks, the vision grew more detailed and more precise. He calculated the energy content of various fuels. He analyzed the efficiency of different nozzle designs. He worked out the mathematics of staging, the principle by which a rocket could shed its empty fuel tanks to become lighter and climb higher. These were not the scribblings of a dreamer, but the systematic investigations of an engineer, and they laid the foundation for everything that would follow. The boy in the cherry tree was becoming a scientist, and his quiet work was only beginning. The Clark University campus in Worcester occupied a gentle rise of land not far from the Goddard family home, and in 1908, Robert Goddard walked its paths as a graduate student in physics. The university was young then, founded barely 2 decades earlier, and its buildings were constructed in a Romanesque style of brownstone and brick, with arched windows and broad staircases that seemed to invite contemplation. The halls were quiet places, smelling of chalk dust and old books, their corridors lined with glass-fronted cabinets containing delicate instruments of brass and glass. Robert moved through this environment with the ease of someone who had finally found his natural habitat. After years of studying in isolation, of working through his calculations alone in his bedroom, he was now surrounded by scholars who understood the language of mathematics and the discipline of experimental physics. Robert's doctoral advisor was a physicist named Arthur Gordon Webster, a man of considerable reputation who had studied under Hermann von Helmholtz in Germany. Webster recognized in Goddard a rare combination of mathematical rigor and mechanical intuition. Under his guidance, Robert designed and built an intricate device known as a magnetic balance, an instrument so sensitive that it could measure the force exerted by a single particle of light. The work was painstaking, requiring hours of adjustment in the dim light of the laboratory, where the slightest vibration could ruin a measurement. Robert found that he loved this meticulous labor, the slow calibration of mirrors and filaments, the patient recording of data in neat columns, the gradual emergence of patterns from the noise of experiment. The years at Clark taught him the discipline that would sustain his rocket work, the understanding that great achievements are built not in dramatic leaps, but in countless small, careful steps. In 1911, Robert Goddard received his doctorate in physics. His dissertation, a study of the magnetic properties of certain crystals, was praised by his examiners for its originality and precision. But even as he satisfied the requirements of his degree, his mind was turning toward the work that truly consumed him. In the evenings, after his laboratory duties were complete, he would sit in his small apartment and fill page after page with calculations about rocket propulsion. He was now developing a comprehensive theory of how a rocket might operate in the vacuum of space, a question that many scientists of the era dismissed as nonsense. The prevailing belief held that a rocket could not function beyond the atmosphere because there would be nothing for its exhaust to push against. Robert, working from Newton's laws of motion, understood that a rocket pushes against its own exhaust, not against the air, and that it would actually work more efficiently in the vacuum of space. This insight, so fundamental to modern astronautics, was then entirely radical. The winter of 1913 was a cold one in Worcester. Snow piled high along the streets, and the trees stood bare against the gray sky, their branches encased in ice that glittered when the weak sun broke through the clouds. Robert continued his work, now teaching undergraduate courses at Clark while pursuing his rocket research in whatever hours he could find. He had begun to think seriously about the practical challenges of building a rocket. What fuel would it use? How would the fuel be fed into the combustion chamber? How could the rocket be stabilized in flight? These questions had no easy answers. Other inventors had experimented with rockets before, but always using solid fuels like gunpowder, which burned too quickly and too violently for controlled flight. Robert had begun to suspect that the future lay in liquid fuels, substances that could be metered precisely, ignited smoothly, and shut off when necessary. It was a radical idea, and it would take years to prove. The laboratory that Robert occupied at Clark was a modest space, a room with high ceilings and tall windows that admitted the pale New England light. Along one wall stood cabinets filled with chemicals in dark glass bottles, their labels written in careful script. On the workbenches lay coils of copper tubing, sheets of brass, and the various small tools of the experimenter's trade. Here, in the quiet hours of the afternoon, Robert conducted his first tentative experiments with rockets. He mixed small quantities of fuel and observed their combustion. He designed nozzles of different shapes and tested them by measuring the force they produced. Most of these experiments failed in one way or another. A nozzle would clog, a fuel would burn unevenly, a measurement would be thrown off by some unaccounted variable. But each failure taught him something, and he recorded every result in his notebooks with the same meticulous care he had brought to his doctoral research. Outside the laboratory windows, the seasons turned. Spring brought green to the campus lawns and the sound of birds returning from their winter migrations. Summer warmed the brick walls of the university buildings and drew students onto the grass with their books. Autumn painted the trees in crimson and gold, recalling the cherry tree of Robert's boyhood vision. And winter returned with its quiet snowfalls, muffling the sounds of the city and wrapping the campus in a hush that was perfect for concentrated thought. Through all these seasons, Robert Goddard worked steadily, a solitary figure in a laboratory filled with the soft hiss of Bunsen burners and the scratch of pen on paper. He asked for no recognition, sought no acclaim. The work itself was enough. The vision that had come to him in the cherry tree had not faded. It had grown sharper and more detailed with each passing year. In 1914, Robert received 2 patents that would prove foundational to the entire future of spaceflight. The first described a rocket using liquid fuel. The second described a multistage rocket, a vehicle that would shed its lower sections as their fuel was exhausted, allowing the upper sections to climb higher than any single-stage rocket could reach. These patents were written in the precise, technical language of the Patent Office, but reading between their lines, one could glimpse the outline of a journey to the stars. Robert filed them quietly, without ceremony, and returned to his laboratory to continue the slow work of bringing his ideas to life. The world at large knew nothing of these patents, nothing of the quiet professor at Clark University who had mapped out the fundamental principles of space travel while the great powers of Europe marched toward war. The contrast between the global turmoil of 1914 and the peaceful, methodical work of Robert Goddard could hardly have been starker. The First World War came and went, and Robert, too frail for military service, continued his research. He developed a prototype rocket weapon for the U.S. Army, a tube-launched projectile that he demonstrated successfully at the Aberdeen Proving Ground in Maryland just days before the armistice ended the conflict. The military, suddenly without an urgent need for new weapons, shelved the project, and Robert returned to Clark with his laboratory intact, but his ambitions undimmed. The war had given him a brief glimpse of official support, but peace returned him to the familiar solitude of his own work. In the years that followed, he would publish a slim volume titled A Method of Reaching Extreme Altitudes, in which he laid out, in careful mathematical detail, the case for rocket exploration of the upper atmosphere and beyond. The Smithsonian Institution, more forward-thinking than most, provided modest funding for his research. The quiet professor was ready to build. In the small town of Auburn, Massachusetts, just south of Worcester, the landscape opened into rolling farmland bordered by stone walls and dotted with old apple orchards. It was here, in the late summer of 1925, that Robert Goddard found a place to build the rocket he had spent a quarter of a century dreaming about. The farm belonged to a distant relative, and it offered what Robert needed most: open space, isolation from curious eyes, and a long, flat field where a rocket could rise without endangering anyone. The farmhouse was a weathered white clapboard structure with a sloping roof and windows that looked out over fields of tall grass that turned golden in the autumn light. Beside the house stood a barn that Robert converted into a workshop, filling it with lathes and drill presses, with tanks of liquid oxygen and gasoline, with the 1,000 small components that would eventually become the world's first liquid fuel rocket. Robert was no longer alone in his work. He had acquired a small team of assistants, a machinist named Henry Sachs who could transform Goddard's detailed sketches into precisely machined metal parts, and a few other helpers who understood the delicate and sometimes dangerous nature of the enterprise. Together, they worked through the shortening days of autumn as the New England countryside transformed around them. The apple trees in the orchard dropped their fruit onto the grass, where it lay in fragrant windfalls until the deer came at dusk to feed. The stone walls that crisscrossed the property grew cold to the touch, and frost began to appear on the grass in the early mornings, glittering like scattered diamonds in the first light of dawn. Inside the workshop, the men bent over their tasks in the glow of electric bulbs, the air thick with the smell of machine oil and the sound of tools shaping metal. The rocket that Robert Goddard designed was, by the standards of what would come later, almost impossibly modest. It stood about 10 feet tall, a slender assembly of aluminum tubes and tanks, with a combustion chamber and nozzle at its base. The fuel was gasoline, carried in a small tank near the top of the rocket. The oxidizer was liquid oxygen, a substance so cold that it boiled at nearly 300 degrees below 0 Fahrenheit and had to be handled with extreme care. The two liquids would be forced into the combustion chamber by pressurized nitrogen gas, where they would mix and ignite, producing a jet of hot gas that would thrust the rocket upward. The entire assembly was supported by a simple framework of pipes that served as a launch stand, and it was protected from the flame of its own exhaust by a cone-shaped metal shield. Every component had been designed and machined by hand, every weld inspected, every fitting tested until Robert was satisfied that it would hold. December arrived, and with it the deep snows of a Massachusetts winter. The fields around the Auburn farm turned white, and the stone walls became dark lines dividing expanses of untouched snow. The workshop grew cold despite the small stove that burned in one corner, and the men worked in heavy coats and gloves, their breath forming clouds in the air. Robert, whose health had never been robust, suffered through the cold with the same quiet determination that had carried him through every challenge of his life. He had waited 27 years for this moment, 27 years since the vision in the cherry tree, and no amount of winter discomfort would slow him now. The rocket took shape slowly, its polished metal surfaces catching the light from the workshop windows, its tanks and tubes and valves coming together into something that had never existed before in human history. The winter passed slowly. January brought deeper cold and heavier snows that drifted against the buildings and required hours of shoveling before work could begin. February was a study in gray, with low clouds that pressed down on the landscape and muffled every sound. Robert used these months for testing the fuel pumps, testing the ignition system, testing the valves that would control the flow of the propellants. Each test revealed new problems to solve, new weaknesses to address. A valve would stick. A fuel line would leak. A pressure gauge would give inconsistent readings. Robert met each setback with patience, diagnosing the problem, redesigning the faulty component, machining a replacement, and testing again. He kept meticulous records of everything, filling notebooks with data and observations, creating a written record of the slow, unglamorous work that precedes any breakthrough. By early March, the rocket was nearly complete. It stood in the workshop like a strange metal flower, its tanks gleaming under the electric lights, its nozzle pointing toward the concrete floor. Outside, the snow had begun to melt, leaving patches of bare ground on the south-facing slopes of the fields. The air carried the first faint suggestion of spring, a softening of the wind that spoke of warmer days to come. Robert and his team prepared for the first launch attempt. They built a simple launch frame in the middle of a frozen field, a steel structure that would hold the rocket upright during ignition. They ran fuel lines and electrical wires across the snow. They rehearsed the countdown procedure, each man learning his role in the sequence that would culminate in the opening of valves and the striking of an igniter. The testing had been thorough, but no one could know for certain what would happen when the moment came. The liquid fuel rocket was an invention without precedent. On the morning of March 16, 1926, the weather over Auburn was cold and clear. A thin layer of snow still covered the ground, crusted over from a freeze during the night. The sky was a pale winter blue, cloudless and calm. Robert Goddard and his crew arrived at the launch site early, their boots crunching on the frozen snow as they made their final preparations. The rocket stood on its launch frame, its metal skin cold to the touch, its tanks filled with gasoline and liquid oxygen that hissed and vented white vapor into the crisp air. Henry Sachs set up a camera on a tripod at a safe distance, aiming its lens toward the launch stand. Robert moved around the rocket with deliberate care, checking every connection, every valve, every fitting. His face showed no excitement, only the focused attention of a man who had waited a lifetime for this moment and intended to get every detail right. A small audience had gathered, Robert's wife Esther, a few assistants, and perhaps a neighbor or two who had noticed the unusual activity on the farm. They stood at a distance, wrapped in heavy coats against the morning chill, their breath forming small clouds in the still air. Robert gave the signal for the final sequence to begin. A blowtorch was lit and placed near the nozzle to serve as an igniter. Valves were opened remotely, and the propellants began to flow. For a moment, nothing happened. Then, with a sound that was more like a sustained roar than an explosion, flame erupted from the nozzle of the rocket. The flame was bright, almost white at its core, and it threw a plume of snow and frozen earth into the air behind it. For 2.5 seconds, the rocket strained against its restraints. Then it rose slowly at first, almost hesitantly, as if testing the possibility of flight, and climbed into the cold March air. The rocket rose from its launch frame with a sound that shattered the silence of the Massachusetts morning, a deep sustained roar that echoed across the frozen fields and sent birds scattering from the bare branches of distant trees. For 2.5 seconds, flame poured from the nozzle in a brilliant white jet, and the slender metal body of the rocket pushed upward against the weight of gravity. It climbed to a height of 41 feet, no higher than a modest tree, and then its fuel was spent, and it curved gently over, descending to the ground 184 feet from where it had started. The entire flight lasted just 2.5 seconds. The rocket had traveled at an average speed of about 60 miles per hour. By the standards of the great rockets that would one day carry humans to the moon, it was almost nothing. But on that cold March morning in 1926, it was everything. For the first time in history, a liquid-fuel rocket had flown. Robert Goddard stood in the snow as the silence rushed back in to fill the space left by the rocket's roar. He watched the thin column of smoke rising from the landing site, watched the steam from the spent liquid oxygen dissipating into the cold air. Henry Sachs was still cranking the handle of his motion picture camera, capturing the aftermath on grainy film that would one day become one of the most important documents in the history of technology. The small group of spectators stood motionless, not quite understanding what they had witnessed, not yet grasping that they had been present at a hinge point in human history. Robert walked across the snow toward the fallen rocket, his boots leaving deep footprints in the crusted surface. He examined the spent machine, noting which parts had held and which had failed, already thinking about the next attempt, the next improvement, the next step upward. The flight had been brief and low, but it had proved the essential principle. Liquid propellants could be used to power a rocket. The fuel and oxidizer could be metered into a combustion chamber at controlled rates. The rocket could rise in stable flight, pushing against nothing but the exhaust of its own burning fuel. Everything that Robert had theorized in his notebooks, everything he had argued in his papers and patents, had been demonstrated on that snowy field. The New York Times had mocked him just a few years earlier, publishing an editorial that claimed he did not understand basic physics because a rocket could not possibly work in the vacuum of space. The Times would not retract that editorial for another 43 years, not until Apollo 11 was already on its way to the moon. But on March 16, 1926, Robert Goddard knew that he had been right, and the quiet satisfaction of that knowledge was worth more to him than any public acclaim. In the days following the launch, Robert returned to his laboratory at Clark University, where the familiar surroundings of chalkboards and laboratory benches welcomed him back. The launch had been a success, but he understood better than anyone how much work remained. The rocket had flown only 41 feet. To reach the upper atmosphere, it would need to fly miles. To reach orbit, it would need to fly hundreds of miles. To reach the moon, it would need to cross 250,000 miles of empty space. The gulf between what he had achieved and what he had dreamed of was still vast. But now he had proof. He had data. He had a film reel that showed a liquid fuel rocket rising from the Earth. He could build on that, improve the design, increase the thrust, solve the problems of guidance and stability. The path forward was clear, even if it would take a lifetime to walk it. Spring came to Massachusetts, melting the last of the snow and turning the fields green again. Robert continued his work, launching more rockets from the Auburn farm over the following months and years. Each flight taught him something new. He learned about the importance of streamlining the rocket body. He learned about the challenges of stabilizing a rocket in flight. He began to experiment with gyroscopes, spinning wheels that could sense deviation from a straight path and send corrective signals to movable vanes in the rocket's exhaust. These experiments were the first steps toward the guidance systems that would one day steer spacecraft across the solar system. The Auburn farm, with its fields and stone walls and patient apple trees, became one of the birthplaces of the space age, though few people at the time recognized it as such. To the neighbors, it was simply the place where the quiet professor from Clark University made strange noises and occasionally set fire to patches of grass. In 1929, a rocket launched from Auburn rose higher than any before it, climbing into the sky with a roar that carried for miles. The flight attracted attention, too much attention. Fire trucks raced toward the farm, their bells clanging. Newspapers sent reporters who wrote sensational stories about the Moon Rocket Man and his dangerous experiments. The local authorities, alarmed by the publicity and concerned about safety, informed Robert that he could no longer launch rockets from the Auburn farm. He needed a new place to work, a place with more space and fewer neighbors, a place where a rocket could rise and fall without attracting the wrong kind of notice. The decision was made for him by the quiet forces of circumstance, but it would lead him to a landscape that seemed almost designed for his purposes, a landscape of vast horizons and empty skies, where the wind blew across open desert and the stars shone with a clarity that New England had never known. Before he left New England, Robert took one last walk through the fields of the Auburn farm. It was autumn again, and the apple trees were heavy with fruit, their leaves beginning to turn. The stone walls that lined the property stood as they had stood for 2 centuries, patient and unchanging. The workshop, now empty of its machinery, echoed with the memory of all the hours he had spent there. Robert was not a sentimental man in the usual sense, but he understood that he was leaving behind a chapter of his life that would never come again. The cherry tree of his boyhood still stood in Worcester, the farmhouse in Auburn still looked out over its peaceful fields, and the stars still shone down every night on the quiet landscape of his youth. But the work required him to move on. The desert waited, and with it, the next phase of a journey that had begun on an October afternoon in 1898, when a boy in a tree had glimpsed the future. The landscape of Roswell, New Mexico in 1930 was a world apart from the green hills of Massachusetts. Here the land stretched flat and endless in every direction, a vast basin of sagebrush and dry grass bounded by distant mountains that rose like purple shadows on the horizon. The sky was enormous, a dome of deep blue that seemed to press down on the earth with the weight of its own immensity. The air was dry and clean, carrying the scent of desert plants and the warm breath of the southwestern wind. When the sun set, it painted the western sky in shades of orange and rose and deep violet, and when darkness fell, the stars emerged with a brilliance that Robert Goddard had only imagined in the light-polluted skies of New England. This was a place where a man could launch rockets and watch them climb until they vanished into the deep blue above, a place where the work of reaching towards space could proceed in the solitude it required. Robert and his wife Esther made their home in a modest house on the edge of Roswell, a town that was then still a small ranching community, far from the bustle of the eastern cities. The house had a porch where Esther often sat in the evenings, watching the sunset color the desert sky while Robert worked late at the launch site miles outside of town. Their life together was quiet and devoted. Esther, who had been his secretary at Clark University when Robert first met her, understood her husband's consuming passion and supported it with a steadiness that matched his own. She photographed his rockets, kept records of his expenditures, and maintained the calm domestic sphere to which he could retreat after long days of work. In the desert, far from the academic communities of the East, they built a life that was simple in its outward forms, but rich in purpose. The launch site was called Eden Valley, a name that carried a certain poetry for a man who believed he was laboring at the beginning of a new human era. It was a flat expanse of desert scrub about 10 miles outside of Roswell, accessible only by a rough dirt road that wound through the sagebrush. Here Robert and his small team built a new workshop, a simple metal building that housed lathes and welding equipment and the growing collection of tools needed for rocket construction. They erected a launch tower, a steel structure that rose above the desert floor and held the rockets upright as they were prepared for flight. They dug a small concrete blockhouse at a safe distance, where observers could shelter during launches and watch through narrow slits as the rockets climbed into the vast New Mexico sky. The facility was primitive by any measure, but it was sufficient. The desert provided what New England could not: space, silence, and the freedom to fail without alarming the neighbors. The rockets that Robert Goddard built in the desert grew steadily larger and more sophisticated. He abandoned the simple pressure-fed design of the early Auburn rockets and developed a turbopump system that could force fuel into the combustion chamber at much higher rates, producing greater thrust. He refined his gyroscopic guidance mechanisms, creating vanes that could deflect the rocket's exhaust stream to correct its course. He experimented with different propellant combinations, always searching for fuels that would burn more efficiently and produce more power per pound of weight. Each new rocket represented months of design and fabrication, weeks of testing and adjustment, and the launch day always brought a mixture of hope and tension. Some rockets flew beautifully, rising thousands of feet into the air before their fuel was spent. Others failed, a gyroscope jammed, a fuel line ruptured, a guidance vane broke loose, and crashed back to the desert floor in pieces. Robert recorded every failure as carefully as every success, learning from each one. The desert seasons turned with their own quiet rhythm. Spring brought wildflowers that appeared almost overnight after the rare rains, carpeting the desert floor in patches of yellow and purple that lasted only a few weeks before the heat returned. Summer was fierce, the sun beating down on the metal buildings of the launch site until they shimmered in the heat haze, the air so hot that the men had to handle their tools with gloves to avoid burning their hands. Autumn brought relief, the temperatures moderating, the light turning golden and long. Winter was mild compared to Massachusetts, though the desert nights could be bitterly cold under the vast immensity of the stars. Robert worked through every season, his health variable but his determination constant. The tuberculosis that had shaped his childhood and young adulthood still lingered in his lungs, and there were days when he could not rise from his bed. But he always returned to the launch site, always climbed the launch tower to inspect a fitting or adjust a valve, always stood in the blockhouse and watched through the narrow slits as another rocket climbed toward the heavens. The world, for the most part, took little notice of the work being done in the New Mexico desert. Robert Goddard published his results in scientific journals, but the popular press had long since moved on from the moon rocket man. The Great Depression consumed the nation's attention, and then the Second World War. Robert offered his rocket technology to the military, and during the war years he moved briefly to Annapolis, Maryland, where he worked on liquid fuel rockets for aircraft takeoff assistance. But the military never fully embraced his ideas, and his most advanced concepts, guidance systems, turbopumps, staging, were not put to use during the conflict. He returned to Roswell when the war ended, his health failing, his work still unfinished, his dream of space still unrealized. The rockets he had built were the most advanced in the world, but the world did not yet understand what they meant. In the last years of his life, Robert Goddard could look up at the New Mexico sky and see the future he had spent his life trying to build. He knew that his rockets were not yet capable of reaching orbit, let alone the moon. But he also knew that the principles he had established, liquid fuel propulsion, gyroscopic guidance, turbopump feeding systems, multistage designs, would one day carry humanity beyond the atmosphere. He had not lived to see that day, but he had done something perhaps more important. He had proved that it was possible. Standing alone in the desert at dusk, watching the stars emerge one by one in the darkening sky, he could take a quiet satisfaction in knowing that he had pointed the way. The cherry tree in Worcester had given him the vision. The workshop in Auburn had given him the proof. The desert in Roswell had given him the space to build. And now the rest was up to those who would come after. In the summer of 1945, Robert Goddard learned that a German rocket had climbed to the edge of space. The V-2, developed by a team of engineers working under Wernher von Braun at Peenemünde on the Baltic coast, had reached an altitude of more than 100 miles, crossing the invisible boundary where the atmosphere thins to nothing and the blackness of space begins. The V-2 was a weapon of war, and it had brought destruction to London and Antwerp in the closing months of the conflict. But it was also the direct descendant of Robert Goddard's work. Its turbopumps, its guidance system, its liquid propellant design, all of these traced their lineage back to the patents Goddard had filed 3 decades earlier. The German engineers had studied his published papers. They had built upon his foundations. And now a rocket had touched space, while the man who had made it possible lay in a hospital bed in Baltimore, his body weakening, his lungs struggling, his work still unacknowledged by the nation he had tried to serve. Robert Goddard died on August 10, 1945, at the age of 62. He passed quietly in his sleep, his wife Esther at his side, the morning light falling gently through the hospital windows. The obituaries noted his contributions to rocketry in brief, understated terms. The world was preoccupied with the end of the war and the dawn of the atomic age, and the death of a quiet physics professor from Massachusetts did not command many headlines. He was buried in Worcester, in the soil of the New England town where he had been born, where he had climbed the cherry tree, where he had first dreamed of machines that could carry humanity beyond the sky. The grave was marked with a simple stone, and for many years, few visitors came to see it. The dreamer had passed from the world, and it seemed for a time that his dream might pass with him. But dreams, once released into the world, have a way of outliving their dreamers. In the years that followed his death, the technology that Robert Goddard had pioneered began to flourish. The United States captured many of the German rocket engineers, including von Braun, and brought them to America to continue their work. At the White Sands Proving Ground in New Mexico, not far from where Goddard had launched his rockets in the desert, the German team tested captured V-2 rockets and began to develop new designs. They studied Goddard's patents. They examined the rockets he had left behind in Roswell. They found, to their astonishment, that the quiet professor had anticipated almost every major feature of their own work: the turbo pumps, the gyroscopic guidance, the steering vanes, the regenerative cooling of the combustion chamber. The debt was acknowledged privately, if not publicly. The path to space had been blazed by a solitary man working in obscurity, and now others would walk it. The years passed, and the rockets grew larger. In 1957, a modified V-2 launched the first artificial satellite into orbit. In 1961, a man rode a rocket into space for the first time. In 1969, two men stood on the surface of the moon and looked back at the Earth, a blue marble suspended in the blackness of space. The rocket that carried them there, the Saturn V, was the most powerful machine ever built by human hands, a towering assembly of metal and fire that rose on a column of flame so bright it turned night into day. And at the heart of that great rocket lay the same principles that Robert Goddard had demonstrated on a snowy field in Auburn, Massachusetts, more than 40 years earlier: liquid fuel, pumped into a combustion chamber, ignited to produce thrust, guided by gyroscopes, shedding stages as it climbed. The cherry tree had borne its fruit at last. The honors came slowly at first, then in greater number. The United States government issued a posthumous patent settlement to Esther Goddard, acknowledging the use of more than 200 of Robert's patents in the nation's missile and space programs. NASA named its Goddard Space Flight Center in Maryland after him, a sprawling campus of laboratories and clean rooms where the technologies of space exploration would continue to advance. A crater on the moon received his name, a permanent mark on the world he had longed to reach. The New York Times, in a moment of belated humility, published a retraction of its 1920 editorial on July 17, 1969, the day after Apollo 11 launched toward the moon. It is now definitely established, the Times wrote, that a rocket can function in a vacuum. The Times regrets the error. It had taken 49 years, but the record had been set straight. What remains, in the end, is not the noise of the rockets, but the quiet of the man who dreamed them. Robert Goddard was never comfortable with fame, never sought the spotlight, never raised his voice. He worked in solitude, in laboratories and workshops and desert launch sites, accompanied only by the tools of his trade and the steady devotion of his wife. He was a man of the 19th century who glimpsed the 20th century's greatest achievement and the 21st century's greatest frontier. He was a man of fragile health and iron will, of gentle manner and fierce intelligence, of a patience so deep that it could sustain him through decades of labor without recognition. He was, above all, a man who looked at the stars and believed, against all the evidence of his era, that human beings could reach them. On a clear night in Worcester, Massachusetts, if you stand in the backyard of a certain old house on Maple Street and look up through the branches of a cherry tree, you can still see the stars that Robert Goddard saw. The tree is old now, its branches heavy with the weight of more than a century, but it still stands. The house is still there, its windows catching the moonlight, its rooms quiet and dark. And if you listen carefully, listen past the distant hum of traffic, past the whisper of the wind in the leaves, you might hear the faint echo of a boy's voice, asking the questions that would shape a lifetime. What lies beyond the sky? Can we go there? How? These questions have no final answer, only an endless unfolding of new horizons, each one discovered by those who dare to look up and wonder. Robert Goddard was the first to ask them in the language of mathematics and metal, the first to translate a boy's dream into a scientist's work. And because he did, we now know that the space between the stars is not empty. It is full of possibility, full of light, full of the quiet music of a dream that never dies.